This video is the second in a two-part series that looks at how a free particle moves in the region outside an uncharged rotating black hole described by the Kerr metric. This second video derives the equations of the geodesics for the radial r and polar angle theta coordinates. It uses the Lagrangian method. So we can find the equations of the geodesics of free particles in the Kerr geometry by using its associated Lagrangian function. So we have a source mass here rotating. We have a free particle of mass m over here. It could be anything, a very small particle, it could be a test mass, it could be a whole spaceship with observers inside. And we have this particle is going to be a free particle that moves along geodesics. Free particles move along geodesics and it will freely fall towards the source mass. Now, as we said in the previous video, it's not possible to have purely radial paths here. In the Kerr geometry, you have the frame dragging effect, which pulls particles off radial paths, and so purely radial paths are not possible. We parameterize the geodesics followed by this free particle in terms of the parameter lambda. It's a general parameter that can be used for particles with mass and without mass. Ideally, for a particle with mass, we would use the proper time. Lambda would be replaced with the proper time of the particle, but by using this affine parameter lambda, we can talk in terms of massless particles such as photons, for which we can't use proper time. So the coordinates of this particle will be x mu is x mu of lambda. The derivatives of each of these coordinates, using the dot here, will be the derivative with respect to lambda, so dx mu d lambda. The fall velocity, which is tangent to the geodesic at all points, has coordinates x mu is dx mu d lambda is ct dot, r dot, theta dot, phi dot, and each one of these t, r, theta, and phi are functions of lambda. Our aim is to find the form of the equations of motion for the other two coordinates. In this second video, r dot and theta dot is our goal here using Lagrangian and one other method. In the previous video, we found the equations of motion for the t dot and phi dot coordinates, the first and last here. So this time we're going to find r dot theta dot. I'll just point out now the fall velocity is tangent. The magnitude of the fall velocity, or the norm squared, the magnitude squared, is u dot u, the scalar product of the fall velocity with itself, the inner product, fall velocity with itself, which gives us minus c squared. For the fall momentum, its magnitude, its inner product or scalar product, is minus m squared c squared. And for a massless particle, the magnitude of the fall velocity squared is 0, and the magnitude of the fall momentum squared is 0. We have a rotating source mass here, bulging in the equatorial plane. So it bulges or dilates away from the rotation axis here. It is symmetrical about the equatorial plane. We'll see about that shortly. Theta's pi and 2, but either half is the geometry is a reflection of the other half about the equatorial plane. All right, so the Lagrangian for a free particle in this geometry is L. Lagrangian's m on 2 times gtt c squared t dot squared, the cross term, the r dot term, theta dot term, and phi dot term here. So gt phi, grr, and the g theta theta, and then g phi phi. Both indices lowered. Now the Euler-Lagrange equations are dd lambda, the derivative dd lambda of the partial derivative dl dx dot mu minus dl dx mu is 0. Now the third coordinate, x2, is theta, and x dot 2 is theta dot. And so if we have a look here, this Lagrangian, and we find the partial derivative of the Lagrangian with respect to theta dot, that's this one here, we'll end up with 2 out front of m on 2 The 2's will cancel. We'll have m times r squared plus a squared cos squared theta times theta dot. That's dl d theta dot. And then we're going to find the derivative of that with respect to lambda, bearing in mind that r, theta, and theta dot are functions of lambda. They're parameterized in terms of the variable lambda. So let's have a look at that now. So the form we seek is dd lambda of dl d theta dot, and then also we'll be after the partial derivative of the Lagrangian with respect to the coordinate theta. All of that set to zero, the Euler-Lagrange equations. Well, coming back to the last result on the previous slide, we need dd lambda of that is dd lambda of this, and we're going to need to use here the chain rule because we have to remember that r, theta, and theta dot are all functions of all parameterized in terms of lambda. So we have 2 times r dot, using the product rule to differentiate this bit first times that, and then that object here times the derivative of theta dot. So then we have a derivative of this theta here. We have to chain rule again. So 2 times a squared cos theta, derivative of that sine theta, there's a minus out front here, times the derivative of this, which is theta dot, and then times theta dot. And then this bit here, the first bit here, times the derivative of theta dot, which gives us theta double dot. So that's the left-hand part here. This next part, dl d theta, now there's theta's running around everywhere, so we have to differentiate fully. I had to do this term by term, bit by term, and then check it with software. That gives me all of this. I'll do all that. Okay. Yeah, so it's quite a bit. You need to make use of the quotient rule there. All right, so putting these two together gives us the equation of motion of the theta component. So we have this part here is equal to, and now this is the part of this bit over here is the partial derivative of the Lagrangian with respect to theta. So I've put that on the right-hand side of the equal sign. You can see it's quite substantial. Okay, now that looks quite imposing. It's quite complex, and that's the nature of trajectories in the Kerr geometry. The equations are quite large and the trajectories are quite complicated. But we can perhaps simplify by looking if for some value of lambda, at some value of lambda, we have theta equals pi on 2. Well, that tells us that implies that cos pi on 2 is 0. And then all of this reduces to, very simply, cos pi on 2. So we're in the equatorial plane now by setting theta equal to lambda on 2. So the particle may pass through the equatorial plane, but at that moment, lambda gives us that value of lambda. We have theta as pi on 2, so cos of pi on 2 is 0. And we can go through and put cos of pi on 2, there will be 0. So anything with a cos term in it will drop off to 0. And what happens then is that everything over the right-hand side of the equal sign here becomes 0 because there is a cos theta term here. And when theta is replaced for pi on 2, they're all going to disappear. And we'll be left with over here, this term here will disappear. This one will, and what we'll be left with is m times 2r r dot times theta dot plus r squared times theta double dot. And if we take this r squared times theta double dot, we take this here, m times 2 times r dot times theta dot over the other side. And then if we divide through by r, we'll end up with theta double dot is minus 2 on r times r dot theta dot. Okay, that's for where lambda is such that theta is pi on 2. Okay, but if we set the polar momentum coordinate, p theta, to 0, so it's m times theta dot is 0, then setting theta dot to 0 here means that theta double dot is 0 and the particle remains in the equatorial plane. So for some value of lambda, we have theta as pi on 2. At that point, we have this equation here, which shows that the particle will continue to move away from the equatorial plane. But if we've set the momentum to be in the theta direction to be 0, m theta dot is 0, then at theta is pi on 2 in the equatorial plane, we can have acceleration there of this coordinate 0, and the particle can remain in the equatorial plane. It simplifies the analysis anyway, as you can see. The other coordinate to look at is x1 is r, so x1 dot is r dot, and the Euler-Lagrange equations dd lambda dl dr dot minus dl dr is 0. Now, dl dr dot is this object. Remember, there was a r dot squared here, and 2 came out front. There was a half, so that cancelled, and we're left with m times this object here. That's dl dr dot. Now, the next thing we're going to be looking for is dd lambda of that. Now, for the next part, we need to be, again, mindful of the chain rule. So dd lambda of Lagrangian or L of a function of r, which is a function of lambda. So let's say we have L, it's a function of r, which is a function of lambda. Then the chain rule says that the derivative with respect to lambda of L is dl dr times dr d lambda. And we have to be mindful of that all throughout. So dd lambda of dl dr dot is m times, okay, and now we have to differentiate this bit by bit. Okay, I had to do this bit by bit and check with the software as well, just to be sure I was on the right track. So what we've got over here, this first part was the use of the quotient rule. Okay, and then the next bit, that was differentiating here. And then the next bit was, because we have to differentiate theta dot, theta and r dot, because they're all a function of lambda. Okay, when we get to the last bit here, that was easy. That r dot there becomes r double dot multiplied by what we originally started with. But this part here was the quotient rule. And then within that quotient rule too, there were derivatives with this r and theta had to be differentiated too with the chain rule. So a great deal of care has to be taken there. All right, then dl dr, the other part, well, there's r's running all through the Lagrangian. So again, differentiating this very carefully bit by bit and with software. All right, there. So need to take a bit of care with this. All right, next we combine the two parts to form the equation of motion for the r coordinate. And so here we go. We have this on the left, and then I'll put everything else on the right there. Quite large, quite complex. All right, now again, restricting motion to the equatorial plane with theta is pi on 2, that implies cos pi on 2 is 0, and theta dot 0, setting that to 0. So setting the theta component momentum to 0, so it remains in the equatorial plane. The equatorial plane being theta is pi on 2. When we do that, it does simplify down a bit, quite a bit, but it's still quite large. Even restricting the motion just to the equatorial plane still leaves quite a large, complex equation. All right, now we can solve for the acceleration of this coordinate in the equatorial plane. We can rearrange it for itself to give us this object here. Again, quite large. Now, the Euler-Lagrange equations have been useful in finding expressions for the derivatives of the t and phi coordinates. That was the first video, but not for the other two. However, there is an easier way to find an expression for the r dot coordinate than using the Lagrangian. So we'll have a look at that. And just to remind ourselves now, for massive particles, the inner product or dot product or scalar product of momentum form a vector with itself. P dot P is mu dot mu. Now let's write this out in terms of basis vectors. Mu mu e mu dot mu nu e nu. There's the basis vectors. Now just collect the basis vectors together and put the components off to the right there. So we've got m squared times the inner product of the basis vectors. Well, the inner product of the basis vectors gives us the metric. M squared times the metric times this. We use the metric to lower one of the indices. m squared u mu mu u mu. And when we do that, we get here this inner product is minus c squared, and with the m squared out front, so minus m squared c squared. So that's the magnitude squared of the scalar product of the momentum forward vector with itself. In the case of massless particles, p dot p is u dot u. What we've done is we've parameterized the momentum in terms of just u mu e mu dot u mu e mu. There's some parameterization of the momentum that allows us to write it like this. I hope you can accept that. It gives us e mu dot e mu. This gives us the metric, and contracting with the metric gives us 0. So both the fall velocity of a photon is magnitude squared is 0, and the fall momentum magnitude of the fall momentum vector is squared is 0 as well. Okay, so in both cases, p dot p is g mu mu p mu contravariant times p contravariant. Contracting that, this should be a mu about that there. That's not a nu, that's a mu. Sorry about that. That should be p mu upper and p mu lower. Really sorry about that. I missed that in the proofreading. Sorry about that. And that can be rewritten as the inverse metric times the component, the lowered covariant forms of the components. Okay, like that. So this and this are equivalent forms. They mean the same thing. For particles restricted to the equatorial plane, the contravariant component p theta is 0. And so we can leave that out. We're now just dealing entirely and only with the equatorial plane. So we're looking at motion in the equatorial plane, as long as we can make that assumption, which we have. We can then expand out this object here in terms of its components, gtt, pt squared, plus 2 times gt phi pt p phi, the cross terms there, both of those. And we have grr, inverse metric there, pr squared, g phi phi p phi squared is alpha. Now, alpha is minus m squared c squared, this one, for massive particles, particles with mass, and alpha equals 0 for massless particles. That's this one here, photons and so on. Right, that's the difference between the two, and that allows us to deal with both cases at once. Just remember that p theta is 0, okay? So the covariant form will be 0 as well. Now, repeating just that equation again, I'm going to work with this one. So we can solve for the radial component of momentum. That's this one. And we just take that, take everything over to the other side. So it'll be alpha minus everything above. So alpha minus all of that. And then we can multiply through by GRR lower, which these two multiplied together just cancel out. So we're left with PR squared is GRR times all of this in parentheses. Now, from earlier, from the first video, PT, P subscript T, P covariant T, it's a covariant index, a lowered index, is minus E on C, P phi is H, PR is MGRR R dot. Okay, and we'll substitute all of that information into here. Okay, so where PT is, we'll put minus E on C. Where P phi is, we'll put H. We found those in the first video. So what we now have is where the PR is, we're going to put in this MGRR R dot, all squared, is equal to GRR times all of that. Okay, and where PT is, we put minus E on C. I didn't put minus in here because it doesn't really matter. It's all going to cancel out anyway, because minus E on C all squared will just give me a positive, so I didn't worry about that. Minus E on C here. Okay, now we get M squared here, GRR squared, R dot squared, GRR, which means that this GRR will cancel out one of these with one factor on the left. So writing that again, this will cancel out one factor. Here we go. Here, that minus E on C was important, so that minus sign here and this minus sign have cancelled, they become a plus. Okay, next stage, we'll cancel out one factor of GRR from both sides. So that one's gone altogether. There's only one here. The way we get rid of that is by multiplying both sides by GRR contravariant. So that these cancel. Reciprocals of each other, which gives us 1. Gives us R dot squared is GRR on M squared. Remember the M squared was divided through here, so we've got M squared there. Now the inverse metric terms are these. That was found in a previous video on the Kerr inverse metric in the Kerr metric series. These were the others, GT phi, written in this form with delta, G theta theta, GRR, delta on R squared, G phi phi, is this object here, 1 on delta, 1 minus 2 GM on C squared. So I've done that because it helps make our life a little bit easier. All right, we can substitute these in where the inverse metric terms appear. Okay, if we expand it out using a software package, this is what you'll get. Putting all the inverse metric terms into that. That's not so bad. It's quite, it's large, but it's not altogether unwieldy. Now we can also write this as, if we don't fully expand it out like I did on the previous line, we can write it like this. Here's the original expression, and we'll put in terms of delta on R squared for GRR, and so on. And we'll put this in GTT, will be this object here. GT phi is this one. Remember, GT phi is a negative, so that's why the minus appears there. And then minus G phi phi is this one here. So a bit more manageable, a bit more compact. Now for massless particles, we'll choose alpha as 0. So remember, this bit dropped off because that was our alpha. And P covariant R, is GRR times R dot. And putting that in, we end up here. Yeah, that's it. Just going through here. And then we'd have made a substitution over on the left-hand side there, but I'll look at that next. All right, that's it, finished.